So what today we are going to do is look at the geometric significance of the Riemann tensor. We have just I've just told you that it's related to the geometry. We're going to see some evidence of it today and perhaps in the next lecture as well. So what does it capture? So we're gonna, let me just not be go, let's not, wait a second. Yeah, let me just uh, start with some informal remarks. So we know that one sign of curvature is that if you start with two parallel lines, they come close or they diverge. So two parallel lines do not remain parallel. Well, they converge or they diverge. Two straight lines, they do not remain parallel. So it should somehow, so if this is a sign of curvature, it should somehow depend on this Riemann tensor. And also, then there's another thing that if you have, like we saw that on a sphere, if I have a vector, I parallelly transport it like this and bring it back. So along a closed loop, when I parallelly transport a vector, I do not get the same vector back. So in other words, the parallel transport is path dependent. Like if I went through this path, I got this vector. And if I directly transport it over here, I'll get this vector. So the vector which I get depends on path. And that's a sign of underlying curvature. So these kinds of things, they depend on the Riemann tensor. And if the Riemann tensor is zero, you do not see these effects. So, and we will also prove that if the Riemann tensor is zero, then everywhere on the manifold, you can choose a coordinate system where the metric takes just the usual flat Euclidean form. So that's also a note that also proves that the Riemann tensor somehow captures the curvature. But how does it capture the curvature? That's encoded in how these vectors are transported around. So this is, I'm gonna just do one such calculation, probably two. But before we do those calculations, we need a little bit of mathematical machinery. I suppose many of you probably know it, but let me just go through it. So if you have this equation, then everyone and their grandma can solve it. It's just, this is the solution, right? With initial condition that at t is equal to t naught, f of t is some value which I'm calling f of t naught. Well, not really. I'll have to have, I can say f of 0 over here. If t is 0, then this is f of 0. In general, I'll have some a alpha t, and I can find this a by giving some initial value over here. Now, suppose if you are given this equation, df of t over dt, and it's very close to your previous equation, but this time this is not a constant, rather it depends on time. Then how can we solve it? Well, we can write a formal solution. I can just integrate this equation and I get some constant of integration, which I'm writing as f of t naught. And I'm just integrating the right hand side, which gives me this factor. And this has the boundary condition that at t is equal to t naught, f of t is equal to f of t naught. Because when I put t is equal to t naught, this integral becomes 0. So this has correct boundary condition if I assume that at t is equal to t naught, f of t is f of t naught. You can think of it, so this comes from direct integration, but I can also think of it as an ansatz which I can check. One can check that this is a solution by differentiating. So I get a 0 here, and then I am differentiate.
सर ये आपने इंटीग्रल में जो dt लिखा है वो t के ऊपर डैश लिखा है आपने?
Dash, exactly, thanks. Then I am taking d by dt of this thing. So when you do this, you just get some, which is the thing which is inside, evaluated at the final limit. I suppose everyone knows it, but let me just quickly argue it, that if f of alpha t f of t is the antiderivative of alpha t f of t, then this integral by the fundamental theorem of calculus, this is just f of alpha t, the antiderivative evaluated at t minus antiderivative evaluated at the lower limit. So now, when I do the, and so my solution is then can be written as plus the antiderivative minus the antiderivative evaluated at t naught. So now if I take the derivative with respect to t, they are both constant. And since this is the antiderivative, I get exactly alpha t f of t. These are just some obvious things. So that means that the above equation is the above solution was the correct solution. But this is all pretty much just the definitions. And it's a very formal solution. How will we get a solution practically? Something which we can deal with, which we can use. So one idea is write the solution order by order in a self-consistent way. So your solution, your equation is this one. This is your solution. Now the issue is that I don't know what is f. F I'm trying to find. So it's implicitly involved, implicitly defined over here. So I cannot integrate it. That's the issue. But I can try to build it up order by order. And I say that at the 0th order, I just take, so you can think of it that I'm starting from t is equal to t naught, and I'm going and trying to build a solution at some value t. I know what is the initial condition, and I'm trying to move forward and get the function at an arbitrary time t. So at the 0th order, you are just assuming that you are very close by. So over here, I can just plug in, instead of the final, whatever solution I'll get, I just plug in the initial value. So at 0th order, you plug in, or you assume, you can assume that f of t is just f of t naught. So at zeroth order, you haven't done really anything. Function is just a constant. But at the next order, you can put it back over here and compute the next order term. T naught plus T naught to T dt dash alpha of T dash and f of T naught. Now you have got this next order solution. Now you take, and note that this is outside the, you can take it to be outside the integral because this is just a constant. Now the idea is that you plug it back over here. You're improving on the solution. You plug it back and you consider the next order, the second order. So what will you get in the second order? F of t naught is just like that, but when you plug this thing in this integral once, you will just have f of t naught, just like that. But then you are also plugging in the integral term. So you will have t naught to t dt dash alpha of t dash, and then this term t naught to t dash, which is coming from this guy. But since I have to plug in the value of the function at t dash, so when I create this f of t, I'm not evaluating the limit of the integral at t, I'm evaluating it at t dash, because I have to plug in an f of t dash on the right hand side. So I take the limit at t dash, then the internal limit, which is just the internal variables, which are just the dummy variables, I just rename them. But this still remain f of t naught. Now I take this thing and plug it back in the equation again. This is just like that. And then again in the integral, wait, I have this t naught t dt dash alpha of t dash, and I'm plugging in this equation, let's call it A, above. So I first have to plug in this integral. That will introduce a double integral. Dash f of t naught. And then I'll be putting in this double integral already, which is a double integral into the integral, which will make it alpha of t double dash, and then t naught t double dash. So these are all nested integrals, but every time I have just an f of t naught. So I can keep doing it. I'll get an infinite series which looks like this. You just keep on increasing the nested integrals. Alpha of t double dash, so on, and outside you have f of t naught. So you can think of it, this thing is also called a propagator. You're starting with your initial condition, and this propagator is telling you how to go to another time t by just multiplying this f of t with this thing. You can think of it as an operator. because all this logic works even if I have functions over here, even if you have operators here, even if you are solving an operator equation, this whole logic so far what I have done actually works. So you keep on doing this infinite series, and now we can check. So we were thinking of it as an approximation, but it's not really an approximation. We can check that this ansatz is an exact solution. Because you can check. I have df over dt. This guy is a constant, so it's remain f of t naught is a constant, remains outside. And when I do this, so as we have argued, we just get the first limit. And then we do this, we remove one integral and just get the upper limit. Then again, you remove the, wait, yeah. So you bring out an alpha of t, you put in the upper limit, this was the third order term, which had now given you two integrals. One integral is removed when you take the derivative, and so on. So you can take alpha of t outside, and inside you have reproduced the same series. I can relabel this guy. This was t naught to t, not t dash. So I can relabel this double dash as dash plus this double integral plus a triple integral, and so on. But this was our ansatz for f of t. So this power series, this series, not power series, this integral series actually solves this equation, and with the correct boundary conditions, because all these integrals, when I put t equals to t naught, they all become zero because I'm matching the upper and lower limit, and f of t takes the value f of t naught. So this thing is actually a solution, exact solution. So it's an exact solution of the equation. Now this is an exact solution, but this solution is still very formal. Still an only formal solution. This is manipulatable because now, well, I shouldn't say formal, formal in inverted commas, because you have at least solved some problem. You have got an ansatz so that on the right hand side, you do not have f implicitly defined. You only have its initial value. So starting from an initial value, you can compute where it goes. But the only trouble is that in this computation, you have an infinite amount of terms. So you want to truncate those terms somehow if you want to be able to compute it realistically. And that will happen. So this is the functional form. Let me see. This is the functional form. In general, you do not have any reason to believe that successive terms will be small and in what sense, unless if you could argue that this alpha has a small parameter in it. If alpha is small in some sense, it has some small parameter, so that in each next term you have terms proportional to alpha square, alpha cube, and so on, then you can truncate the series to any given accuracy in the small parameter, which is hidden in alpha, or if alpha is somehow small. So that's the that is when it becomes useful. So this is called also perturbative expansion. By the way, just a side note, this same integral, you can give it another shape. I think we will not be using it in our calculation, but let me just mention it. You have this integral, double integral. For example, if I look at this term, t naught to t dt dash alpha of t dash t naught to t dash alpha dt double dash alpha of t double dash. This is the integral we are trying to evaluate, and it's a double integral. So what kind of double integral is this? Let me just, for ease of looking at this diagram, let's put t naught equal to 0. We can just shift it, doesn't matter, or you can draw the diagram at a slightly shifted place. So you have a t dash plotted here, t double dash plotted here. And what this integral is telling you is that if I fix a t dash, let's say if I fix this value of t dash, I have to integrate along t double dash up to when its t dash value equal to t dash. T double dash value becomes equal to t dash. When I am at this value of t dash, again I integrate t double dash up to this place, and so on until I reach. And where do I integrate t dash up to? From 0 to t, final value. So you are integrating, if I look at it as a double integral, integration over an area defined by these two variables, then it is this triangle that I am, right triangle, that I am integrating over. But now you can free this integral, this nested integral, you can free it up by noting that alpha of t dash times alpha of t double dash. So I can just look at these two things, and I want to try to write them something like this. dt dash dt double dash up to some integration as this kind of a function, because I'm integrating over this area. So I note that this is equal to, if I flip the coordinates, so that means if I had reversed the role of t dash and t double dash, I'll still get the same integral, because it will be just renaming, because there's no difference in this reversed order. So I can extend this integral. I can replace it by this integral. So this integral gets replaced by this one. Integrate over the whole square. So that means you are freely integrating over t dash and t double dash from t naught to t, t naught to t, and t naught to t in both variables. And you are integrating these guys. But you have just doubled your value of integration. Whatever value you will get here will be exactly same over here because of this property. So you better divide by half. Similarly, if you look at the next term, you will have a cube. You are integrating over a portion of a cube, which you can extend it to the whole cube in 3 variables, and you find that you are overcounting by 6. So you can replace the next integral by this thing. So this was our original integral. This you can replace by 1 over 3 factorial t naught to t, t naught to t, dt dash an unnested integral. And since it involves imagining some cubes, etc., you don't have to take my word because it's very easy to check that if I write this ansatz, which this transformed ansatz, alpha of t dash plus half dt dash alpha of t dash t naught to t dt double dash alpha of t double dash plus 1 over 3 factorial and so on. Now you can see, and outside is multiplied by f of t naught. Now you can see that when I will take a derivative, again, one will be removed. From here, I'll just get alpha of t. But when I hit the next term, I don't just remove one integral because both integral have limit t. So they become, these two things become functions, two functions being multiplied of t. So I have to use the Leibniz rule. And when I use the Leibniz rule, the first term gives me alpha of t, t naught to t, dt double dash, which I'm gonna just relabel and call it alpha of t dash. And the next term, again, it leaves this integral, but takes the derivative of this and evaluates it at t. So it again gives me alpha of t, t naught to t, dt dash, alpha of t dash. So this half is absorbed. And at the next level, I have three integrals. So when I derivate this, I get two double integrals left and an alpha of t reproduced. But I have to do it three times. I get this multiplied by 3, which removes this 3. And you can imagine that at the next level, this is why this factorial is coming up. You will be having 4 similar terms when you derivate, which takes away this 4 to leave you a 3 factorial. So we have checked that this is actually a solution. So this solution you can formally write, because this is exactly an exponential. So this has the same form as your original solution. Instead of having the alpha in the exponential, you have alpha times dt, which is being integrated. If this alpha is constant, you can check that this gives you exactly your normal solution, because this alpha will come out and you will have a t, so you get an alpha of t. But this is a solution for any of this equation, where alpha depends on t. This kind of solution, and again, this is useful only in formal manipulation, or if you can expand in some small parameter. Just a side remark, because if you ever take Lie algebras or even quantum mechanics, time dependent quantum mechanics, if you look over here, wait, when I argued that alpha of t dash times alpha of t double dash is equal to alpha of t double dash, this equation, this is actually not true. This will not be true if they do not commute. If alphas of t's are non-commuting operators. So there could be operators or matrices which just do not commute at different times. At different times, you're getting different operators and they do not commute. And what you have in the original equation, you have this ordering, because you had put in alpha of t dash first and then the nested integral and alpha of t dash coming again. You will be able to remove this nested integral by including this other strip. If you could say that on this side, I'm again going to do the same thing. But how will you be able to do it? If you force it that whenever I have these guys, because in this integration, t double dash comes first and then t comes. Whenever I have this, I'll give them the ordering, whichever is first in time comes first. So then this formally becomes a time ordered exponential. Some people call it path ordered exponential. I know this part is very quick, but we don't need it because we are just dealing with the functions. Now, with this little technique at our hand, let us look at the calculation which I want to do. So now let us consider that you have, is there any question?
No, sir.
So how many people, just asking, how many people had seen, maybe you are doing these integral equations, how many people had seen this solution? Has anyone seen it?
Not yet, sir.
किसी ने नहीं देखा हुआ
इंटीग्रल इनइक्वालिटीज में तो देखा है इस तरीके का, वो फैक्टर ये जो बनता है,
मतलब कि as a solution of this differential equation, have you seen it?
नहीं सर, पर्टिकुलरली इसके लिए तो मैंने,
अच्छा, ठीक है. So now let us consider that you have a vector v mu at some point, and you want to parallelly transport it and bring it back, and you want to see where does it go. Does it come back or does it give you something else? And our idea is that if it depends on the path, then we will say that or if I take a loop and it doesn't come back to itself, then we will say that there is some curvature. Because if it doesn't come back to itself, मैं इसको ऐसे भी देख सकता हूँ कि मैं यहाँ लेके जाऊँ, I get this one, और मैं इसको यहाँ से यहाँ ले जाऊँ, I get this some other one. When I reverse this path, I'll get this one, because यहाँ से जाके मैं यहाँ आया था. लेकिन अगर मैं इसको यहाँ पे ले आऊँ, इस वाले को, orange वाले को, so it will end up at some other path, at some other vector. So these two things are equivalent. If I say that if I go in a loop, come back and I do not get the same vector, it is saying as the same thing as if I take different paths, I'll get different vectors. Or in other words, if I go in a loop and if I get the same vector for any loop, I always come back to the same vector, then I can split this loop over here, then I'll go along this path or this path, I will end up with same vector. So that would be a sign that you have no intrinsic curvature in your space. Now, we know that in case of curvature, these things are going to depend on path. So that is fine. And I want to define the curvature locally at each point. So because the space could be bent differently at this point and this point. So I make a loop and try to see how these vectors change, but I make a very small loop because in the end, I'm going to shrink this loop to 0 size and extract the information about what's happening in the very small neighborhood of this point. So that's the idea. Make small loops and let this vector be parallelly transported along this loop, come back to the same point and see if you get the same vector or not. And if you don't, what does it depend on? How can we, in general, compute it, that what kind of vector we will get? So I'm parallelly transporting. We are parallelly transporting. And the vector is v mu and curve is x mu of tau. So I can also write the tangent vector of the curve. So the parallel transport equation then tells me the T mu d mu V alpha is going to be 0. Let me write it this way. The covariant derivative computed along the curve is 0. So dx alpha over d tau, d by dx alpha v mu plus these terms is 0. And then this gives me dv mu over d tau is equal to gamma mu alpha beta v beta dx alpha over d tau. Now these coefficients, they depend on these ones. They depend on the tau. Let me write it this way. Let's write it on the other side. This is just the initial vector which have come over here. While these guys, Christoffel symbols, because the metric is changing from time to time and Christoffel symbols are just the derivatives of the metric, so they can take different values along the path. And similarly, the tangent vector of the path is varying from point to point. So these two things depend on the parameter along the path. So then this becomes an equation of the form which we just wrote for these objects. This is alpha of tau v mu, something like that. So then we have just figured out how to write a solution for this. So the solution would be the initial value of this v mu minus, because there's a minus, I'm just writing it outside, t naught to tau gamma mu alpha beta tau dash. This is just that function alpha, and it's contracted appropriately to give you a mu over here. Plus, now I have two negatives, so they get absorbed over here. Gamma mu alpha beta d, and this depends on t dash, dx alpha over d tau, d, this depends on tau dash. Then this gets contracted with this guy, and these guys depend on another dummy variable, and there's a double integral, and this finally gets contracted with the starting value of v nu. Now we are assuming we want to expand it, we want to write it, it just keeps going. So we just take some coordinates where you have these Christoffels are small. So you are near, so at the starting point, you take this to be eta or just delta mu nu. So close by the Christoffels, because they are built up of from the derivatives of the g, and since you are very, very close, you are expanding this g in a Taylor series around it, which is well defined, and these derivatives are going to be small. So I'm assuming that if I don't go far away, I'm making small curves, these gamma mu nu, gamma mu alpha beta themselves are going to be small. They're going to be small, and so then I'm going to expand this term in this small gamma mu alpha beta. So I'm going to drop higher order terms have third powers of gamma, so drop higher order terms. Drop them is justified because in the end, I'm just going to take a limit. So it won't even kind of matter. Now, they're small, but they're still varying from place to place because I have to integrate them along some curve. So I need to see their dependence on how they change from place to place. So I have to expand them themselves. So it's like this. They change from place to place. They're defined at each point in a particular coordinate system. I want to look at them along the path. So they depend on the path through this coordinate. So it would be some kind of a Taylor series starting from x naught, its initial value, where x naught is the point which is at tau naught, where you are starting from. And then you have rho at x naught and so on. And you are assuming that this Taylor series is convergent. Each derivative is just smaller than the next because the metric is being expanded like this. Now, the linear term, this term, will get contribution only from the first integral. So the first integral over here, when I'll plug this value in, I'll have something, I'll have an integration coming from this x dependence, but from this, there will be no integration on, at least on the Christoffels. So if I collect those terms by plugging in over here, I have gamma mu alpha beta x naught, this just comes out. And this v beta is outside. It's also is not depending on the integral. So this is what I get from this term, plugging in the first one. Now, so this gives me this guy, this integral. Is just this. And for the closed loop, I come back, tau brings me back. Tau is a different parameter when I come back, but x of tau is equal to x of tau naught. So this is 0. So this whole contribution goes to 0. But then we have this term, coming from the derivative term, this term. When I plug it over here, it's evaluated at a point, so this comes out. And inside, you have dx alpha over d tau v beta of tau naught. So the integral I'm trying to evaluate is this. Tau naught tau d tau dash x of tau dash this part of the integral, this part, this is just the sum of two integrals. This is constant, so this is just like the previous integral. This is just this integral. So the constant term does not contribute because this is a total derivative, and on a closed loop, it gives me 0. But I'm left with this guy. So this integral is there, and I'm gonna see what I can do about it later. But let me just note that I can put in, because I have this second order term coming in. So I can get a term from this equation as well. From this equation, I can have one linear term in gamma and one term involving no derivative of this Christoffel and one term involving a derivative of the Christoffel. The term involving two derivatives, I'm gonna drop it out because I'm assuming that each term in the Taylor series is becoming smaller and smaller. So the more derivatives you have, the smaller the contribution is. So I'm not going to that order. So you are left with this term. From the second integral, from the term involving two integrals, you have gamma mu alpha beta gamma beta uh, sigma. Well, oh, I misspoke. What I need to do is collect the constant terms because constant is first order and the first derivative is second order. So if I multiply two constant terms, I get something second order, which is the same order as this guy, the first derivative. This term is proportional to first derivative. If I include one constant and one derivative, that's already one derivative is second order and one constant is first order. I'm already in the third order. So I'm dropping that. And I'm only keeping the both first order terms. So I'll have these guys evaluated at x naught. And we knew, which I have written over here, and these double integral. And actually I'm writing it as a nested one. And I know when I write it as a nested one, I don't need the two. Now this integral, I can wait. I can do this integral. When I do this integral, what do I get? So let's look at this full integral. Tau and when I do this integral, I'm get x sigma at tau dash minus x sigma at tau naught. And we know that we can drop this constant term. This is not going to contribute when we do this integral and put tau naught equal to tau is equal to tau naught. When I come back to a full loop, this term is not going to contribute. And I'm left with the exactly the same term which I got from the previous integral. Involving one derivative of the coordinate and the coordinate itself. But this term, I just note one thing. This term is antisymmetric. In its integral, in its indices. Because if I look at d tau dash dx alpha over d tau dash x sigma, and I add to it dx sigma over d tau dash x alpha, then this is a total derivative. And when I'll integrate it on a closed loop, I'll get a 0. Was there a comment?
यस सर, ऊपर वाले इंटीग्रल में डी टॉ डैश आएगा ना, एक
कौन से वाले में?
इस वाले में इसमें ये पर्पल में लिखे हैं।
ये
हाँ हाँ, इसमें
टॉ डैश ही लिखा हुआ। कौन सा ये?
नहीं
लिमिट?
जी नहीं नहीं नहीं, अलग से डी टॉ डैश जैसे नीचे लिखा हुआ है ना।
हाँ यार, ये इतना तो आप खुद ही लिख ले सकते हैं। तो so this is equal to 0. So this means tau naught tau d tau dash dx alpha when I have reversed. So if I reverse the indices, the integral changes the sign. Only for a closed loop. I'm not writing this tau as tau naught because that gives the confusion as if the integral is 0 because I didn't do anything, but it's not that. I'm starting from tau naught and coming back to tau, but at the same point. But since I'm at the same point, I get this thing equal to 0, and the integral is then antisymmetric. So if this is antisymmetric, I can collect these terms. No, this is a mess. Not really. I have rho alpha here. Let me write. D rho, let me see. Gamma mu alpha beta. Mu alpha beta. D rho gamma mu alpha beta. And it's being multiplied by this integral. V was contracted to, it's not written in my notes, that's why I have to copy from here. Yeah, V was contracted with beta, and the derivative term was contracted to alpha. And over here, I have x rho. This is one term, and this term was with a negative sign. Let me see. I don't know what this thing is doing. Yeah, it is this term, so it comes with a negative sign. And the other term came with a positive sign, and it had a double gamma mu alpha beta, gamma beta sigma nu. Gamma beta sigma nu. And it was multiplied. V was contracted with nu, and alpha and sigma. Alpha on the derivative. X sigma. This is a integral. Now these integrals would be same if I call this sigma. Sigma is a summed index. So I'm just gonna call it rho so then you can take this common. This was I did something wrong. This was new, and this sigma was replaced with rho. Gamma, beta, rho new, and this integral and multiplied with v of beta. But to do that, I have a triple. So this is a summed one. I can replace it with something else. Give me a good thing. What the heck? Yeah, that's okay. This I put as beta. And over here, I have to put a summed index. So I still have a sigma available. Yeah. Everything is fine now. Okay. Now, I know that this guy is antisymmetric in alpha and rho. So that means I can remove the symmetric part from it, and I can the thing multiplying it will be only pick up its antisymmetric part. This we have learned, right? So I have to just include rho beta plus gamma mu alpha sigma gamma sigma rho beta minus gamma mu alpha and rho are being replaced. And just include a half. This is perfectly legitimate because one guy over here is antisymmetric. Now, but this guy over here, if you look back into the notes, this is exactly the definition. If I take a minus outside, this is exactly the definition of, so there's a half. This is exactly rho mu I'm contracting with beta and rho alpha rho down dash and v beta. So your v mu tau, when you have come back, minus v mu, because this was also there on the right hand side, is equal to to the first order. The other term was 0, and this is the first non-zero order in our expansion, is computed to, so let me write it just as a contour, as a closed integral, and x rho dx alpha over d tau dash. This contracted into this guy. So what it's telling me that if Riemann is 0, then the vector components will match after a detour along a closed curve. And if not, then it is actually the Riemann. Riemann controls how the vectors match when you go around the circle. Not only that, but also because I can split this circle. So if I start from here, whatever this vector goes when I go to path 2 is same as if I had this vector which I had taken from here to from point P to Q. If I take it along path 2 and I bring it back, I'll get the same vector. So just this statement, as I had said before, that I start with vector and I receive this back, is equivalent to saying that if I take this path or if I take this path, I get different vectors over here. So this fact as well, that two different paths take me to different final vectors, depends on the Riemann. If Riemann is 0, then along closed paths, I do not get a change. So that also means that if I start from one point, I can take any path. Path 1 or path 2, I'll get the same vector. So the parallel transport, in case of zero curvature, zero Riemann tensor, becomes path independent. Let me write it here. Parallel transport becomes path independent in case of zero curvature or zero Riemann components. And this guy, this you can think of it as a kind of area of the closed loop. I'm not going to go into the theory of the two forms, but if you just open it up, like for example, write it for Cartesian, this is pretty much the area of this closed curve. So you can divide by this term. So you are taking small tour and then you divide by this area. So it tells you how the vector behaves. So that means this guy has units of kind of area to the -2. This is a length, this is a length. So you have area over here. Vectors remain on both sides. So this guy should have units of area -2. So this, if I divide by this area, by this, so I'm doing this limiting process. So it tells me that for a vanishing path, even if I take a vanishing path, my vector changes because it depends on the second order derivative of the metric, which is non-zero. And how does it changes? It changes its control through this Riemann tensor. So in other words, Riemann tensor is the differential measure of the curvature. It's the process of taking a vector along a closed loop, and that depends on the what path you take, but it also depends on how much is the area of that closed loop. So in the limiting process, when you make this path very, very small, then it becomes like something quantity defined at that point, and you make it area independent by dividing this area. And since this path is very small, then it doesn't matter which path you take, and you're left with something proportional to a tensor. So this tensor is essentially measuring how the uh, vectors move around on small curves. How do they change? So it's a measure of curvature at a point, at a single point. Now, there are many, many more things which can be said about it. I'll probably say a few more, but one small thing, because we don't have much time now, is the following. This Riemann, because it's actually the curvature also controls how the geodesics, which are the straight line, do they remain parallel or not? By the way, is there any question?
No, sir.
Okay, so suppose you have, now we know that if you have like parallel lines which are initially parallel, they will remain parallel in flat space, but if it's curved, they may converge or they may diverge like that. So this is what I'm going to study, that how can I tell if they are converging or remaining parallel. So I take a family of these geodesics. So consider a family of geodesics. So there's a parameter along these geodesics, which I'm calling tau. And on each one, I give it a same name, tau. And I label the geodesics by another parameter. So you can think of it like it's a continuous family of geodesics. So I label each geodesic by some value of this other parameter, S. So you have kind of a threading like this. It's up to you how you want to thread. You call this geodesic S1, this is S2, and then you want to say that how the parameter tau on S2 at this point is labeled. It's up to you. You can just do it in any way, and you will create a mesh. So this gives you a 2D surface, which you have pretty much parameterized, or you can think of it, you have put 2D coordinates on this surface, which are these. Let me call it, instead of tau, let me call it T, because that's an S, T and S. And they are pretty arbitrary, except that this T is an affine parameter. Apart from that, they are pretty arbitrary where you start on the next geodesic, because it's completely independent of what happens on the first geodesic. I can call this one and I can call this one. You just know, because you know that this one is not that one, because you have a corresponding S parameter which labels this point. So now I want to know how does I define, so when I go from one geodesic to the other, I can define a vector which points from one to the other. And it tells me if I go to a nearby geodesic, how do I do that? So that is S mu, which is dx mu, these are the coordinates in the n-dimensional space, ds. So these are the curves which take me from one geodesic to the other. And this vector essentially tells me how they link. अगर यहाँ पे tau की वैल्यू 1 है तो यहाँ पे ये कैसे, यहाँ पे कौन सा कोऑर्डिनेट होगा, अगर यहाँ पे एक सर्टेन कोऑर्डिनेट तो यहाँ पे कौन सा होगा. So this vector, you can call it the I don't know, what should I call it, linking vector. It links one geodesic to the other. Let me see, what is the book calling it? Yeah, it's calling it deviation vector. I don't know, that's a good name. But anyway, it's the linking vector. Now I can compute, for example, I can define this kind of velocity. It's not a velocity, let me just put it in inverted comma. It tells me that I have this linking vector. How does it change as I move along my geodesic? So in other words, I'm going to use it to see if they remain parallel or not. So I have this vector pointing in this direction, and I move along my geodesic, along tau, along t, and see if I get, so I parallelly transport this linking vector, and if I see if I get the same vector, if I take this vector, this linking vector over here, is it being parallelly transported by the field which is defined through these S mu, because these are a field. So that means if they're changing or not. If they are not changing, if it's the same vector, then I can say that these lines are remaining parallel. So this is what I'm going to compute. That when I go in the direction of t, how does this S mu change? So this t rho is dx mu over dt. I'm using the same symbol for the vectors as the corresponding parameter. And S mu, as I have written over here, is ds. But this is not a good measure because I don't know if they are initially parallel or not. Even in flat space, if I take these two lines, these are straight lines, and there's nothing like about the curvature of the space which is making them depart. It's just that they're not parallel. And for lines which are at a distance, I don't know how to define parallelism. So in this case as well, the vector will change. Or you can even see that if I just do this, that I parameterize the tau over here differently, these vectors will be pointing in different directions. So this is not a good parameter. What is good is its next derivative. That I take this velocity. So these are changing as I move along the geodesic. But they are changing just because this line is tilted. They both have affine parameters. So whatever the relation is, that's linear. But if this line is curving away because of curvature, this v mu which I will get will not remain constant. So I have t nu d nu of v mu. The second derivative should tell me if these lines are remaining parallel or not. Because if v mu is 0 initially, that's okay. But if there's an acceleration, so v mu which is 0 initially, it means these linking vectors are all pointing initially in the same direction. So the v mu, the change in them is 0. But if they are diverging away, the initial change is 0, but that change is changing, which will be captured by the acceleration. So that's the idea. Because just having the first change not equal to 0 does not capture it. The second does. Now we want to compute this, but before I compute it, I need a very small result. So we know that this thing, if I compute this thing, this is obviously true. It's just the partials commute. But this guy, the first derivative, is just t mu. And this is d by dt of s mu. This is the same equation. Now, if I look at this guy, s nu d nu t mu, then this is s nu d by dx nu t mu plus s nu d mu nu sigma t sigma, and this, because it's the partial, so this gives me, sorry, this is s, this gives me d by ds of t mu Now, if I compare it with this guy, oh, it's not. T nu d nu s mu, then again, using the same logic, I get this time d s mu over dt plus gamma mu nu sigma. Nu this time gets contracted with t nu and sigma with s sigma. So I'm gonna see that if they are equal or not. So this is just dx mu ds dt, and this is just dx mu dt ds. So they are indeed equal, these two terms, they cancel. This is just the partial property. While for these guys, on the right hand side, for example, I can replace nu with sigma. But the Christoffels are symmetric. That's why this geometry, when you have torsion equal to 0, is much, much simpler. So Christoffels are symmetric, so these two terms are same. So that means these two are same. So S nu d nu t mu is t nu d nu s mu. I can replace them. This is true whenever you have these vectors, these tangent vectors coming from a coordinate, which is being over here, and these are actually the S and T are defined to some coordinate mesh. But in any case, this is true for us. Now, using this, I can compute very quickly this deviation acceleration. Well, this S mu, I think people do call it the deviation vector. It just means how this other thing is deviating away. But what is more meaningful is its second derivative. So I get this. This is just the definition of A. Now I use this here. D rho, and this becomes S nu D nu T mu. And now I just use the Leibniz rule for the covariant. So I get D rho S nu D nu T mu plus T rho S nu comes out and D rho acts on D nu T mu. So now since I have two covariants acting on a vector, then I know that this must be proportional to the Riemann, because I have this d rho d nu minus d nu d rho t mu is actually the definition of the Riemann. So I have d rho d nu over here. I just bring this to the other side and replace it to bring the Riemann tensor in over here. So I have T rho d rho as nu d nu T mu plus T rho as nu d nu d rho T mu plus sigma rho nu T sigma. Now, what do I do? Nu T mu. Now I know I use the Leibniz rule in the reverse direction, because I know I have this guy over here. This guy acting over here. So I want to bring this derivative, which is acting over here, I want to bring it out somehow so that I can cancel some things. So, and I want to include it in here, this T, because I'm going to use the fact that these are parallel, these are geodesics, so that this equation is satisfied. T rho, D rho, T mu is 0. This is the geodesic equation. That the tangent vector of the line itself is being parallelly transported along the line. So I just do this in the reverse. If I look at this guy, this is D rho T D rho T mu. Well, let me D nu T rho D rho T mu and plus T rho there's a little bit T0 plus T0 d nu d-rho T mu. So that means this guy, this thing is written over here. I can replace with these two terms. So I get from here T rho d rho S nu d nu T mu plus S nu d nu T rho d rho T mu minus S nu d nu T rho d rho T mu, because this term came with a minus sign, and plus R mu sigma rho nu. T is dotted into sigma, and the other ones are like this. T dotted twice, and there's a sigma. But this guy is 0 because T is parallelly transported. T is because they are geodesics. T is a tangent of geodesics. While over here, I can again use my starting equation that this must be equal to, this was here, this must be equal to d nu SO. But these two terms are same. If I replace rho by nu, they're same. So they cancel. And I find that my A mu is just proportional to the Riemann tensor. So I have to provide, I'm talking about which geodesics I'm checking, if they're coming close or not. So I have provide there, and it's happening at a point, like very nearby geodesics. So I provide this T, and I provide how I'm linking these geodesics. Are they initially parallel or not? So it controls if they move away or if they move closer. So these are some of the geometric properties of the Riemann, and they just show that the Riemann controls the geometry of spaces. Two things we have seen: how the vectors depend on path during their parallel transport. So this is related to if a vector comes back to itself after a detour. We had seen that if we make a sphere, we had computed it the other day. Parallelly transport a vector over here, it doesn't come back to itself. It only comes back to itself on the equator, not otherwise. And that is also that on the equator it comes back because of some coincidence, that there's a, it depends on a cosine, and that has a period which matches and it gives it back. So if a vector comes back to itself after a detour, and also it controls how parallel lines diverge or converge. So any question?
सर मुझे तो नहीं.
So we have 4 lectures left, but we have kind of missed because I think I'll probably be able to complete the minimum which we need in 5 or maybe 6. So you have to bear with me and take some more lectures in the next 2 weeks. And then hopefully we will be able to write the Einstein's equations. We are very near them, but we need about 5 lectures worth of material to do it.
Okay, sir.
So let me stop here.
सर फाइनल पेपर के बारे में भी
हाँ,
डिस्कस कर
फाइनल
रहे हैं
पेपर के बारे में ये है कि it will be take home.
ये
Okay, sir.
कंफर्म है
Confirm है. Take home का मतलब ये है कि you will have enough time. It won't be like कि आपने अभी 3 घंटे में देना है. अभी मैंने आपको एक assignment और दूंगा, so you should do that. And apart from that, you should think of it, the final, as another assignment, essentially. I'll give you enough time to do it. About
Okay,
a week or something.
Okay, sir. Thank you very much, sir.
Okay.
Thank you, sir.